Okay, the next topic we're going to go through is two variable and break-even problems. And since I am not in the classroom to help you, I wanted to at least help set up and discuss a couple of these problems before you jump to method test prep and complete those 5 problems. Now, this first problem we have for a gardening project. Samuel purchases large bushes, which cost $40 each, and small bushes, which cost $25 each. Now, if he buys 18 bushes in all and spends a total of $555, how many bushes did Samuel purchase? Now, if you were in the live session last Thursday, one of the strategies we discussed was to be very comfortable with systems of equations. And as always, plugging in numbers is going to be big. So the first thing, you really just want to think about, what do we want to know? What do we want to know? And what we need to know is the number of small bushes. So let's just call X the number of small bushes. And you can pick any variable you want, but let's just call Y the number of large bushes. Now, what you do know is that he bought 18 bushes in total. So what you need to do is just set up a little equation, and it's going to be systems of equations. So I like to stack them, write them on top of each other. And now we can attach a price to these. So we know, let's see here, $25 for the small bushes. So 25 times the small bushes plus, we don't know how many of these yet, but we know the total. And we know that the large bushes are 40. So 40 times Y, and the total price is $555. So now we have a nice little systems of equations that we can easily manipulate and solve. I think here, when we have, a 1 in front of these numbers and 25 and 40 are fairly large, substitution is going to be key. So it doesn't matter which one you solve for. Maybe you want to solve for Y, so we can move the X over, and we get 18 minus X. Now I know what Y is, so I'm going to take this 18 minus X. I'll plug it right in for Y, distribute, solve for X, and you are good to go. Actually, now that I'm thinking about it, we do want to solve for Y initially because we want to get rid of Y. We only care about the number of small bushes, and I did say that X is the small bushes, so we should definitely solve for Y. I kind of got lucky there. But also there are break-even problems, and number 2 is the first example of what a break-even problem is. And they're called break-even problems because they're basically asking you at which point are the two quantities equal, or sometimes slightly past equal. So you're going to want to set it up the same way. And sometimes you'll have greater than equal to or less than equal to help you solve. And I'm going to go through some of those examples here, but I just wanted to discuss that before moving on. Okay, so this example is a grid-in, and this is a question that could be asked in 2 different ways, and I'll show you the second way after we solve this, but by doing it this way, we're going to also do it the other way, so this will make the most sense. So County X in 2014, key to note that, had 783 miles of paved roads, and starting in 2015, the county has been building 8 miles of new paved roads each year. At this rate, how many miles of paved roads will County X have in 2030? So right away, just like I said in the last example, the first thing I want to decide is what variables I want to define. Now, the number of paved roads are going to depend on the year, and we know that the number of years after 2014, we're just going to represent You can use any variable, but when we're talking about number of years, I'm just going to use the letter n. And we know we originally start with 783, and then no roads or no paved roads go out of service, so we're not going to lose any. So we have 783 plus 8 per year, so there are 8 per year. So therefore, each year we just add 8. So now what we need to do is we need to figure out how many years we're taking into account. So we have 2030 is when we start, or when we end, and 2014 is when we start, and that gives us a total of 16 years. So now 783 plus 8 times 16. Grab my calculator. I'm going to plug that in. And we should get 911. So on your grid in, there would be that would be your answer. And now what they could ask you to do is to come up with an equation to represent that, which we can see here. And like in this problem, I had 783 plus 8n going to be the same here. So this would be choice C. Building off of those examples, we have a similar problem, but here it's asked in the break-even form. So in 2014, County X had 783 miles of paved roads. Starting in 2015, just like the last examples, 8 miles per each year. At this rate, in which year will County X first have at least 1,000 miles of paved roads? Assume no paved roads go out of service. Now, for here, we have to create and solve an inequality. In example 1, where we just did, we said 783 plus 8n. But now we want to know when there will be first be the 1,000 miles of paved roads. So now, instead of just having a function, we can say 783 plus 8n is greater than or equal to 1,000, because this number with no units or variables is just the miles of roads. So same with 1,000. Now, what this does, if we solve for n, we get 8n greater than or equal to, and do this, 217. Then we want to solve for n because we want to know the number of years. So 217 divided by 8. So n is greater than or equal to 27.125. Now this is where it gets tricky and you have to really think about it, because you really have to focus on what these numbers actually mean. So what it means is, from the moment we start paving these roads, 27.125 years later, we have 1,000 miles of paved road, which is good. But we start in 2014, and this takes 27.125 years to occur. So what that gives us, if we add these together, is 2,041.125. Sorry, I had to double check that math. But this doesn't make sense, because if there is a little fraction at the end of the year, that means it takes longer than that time. So this would most likely be in the beginning of 2042, where we would hit this milestone of 1,000 roads. Problem I wanted to include, because this one incorporates percents, which is something we've seen come up over and over again. So Mesa bought a pair of pants and a briefcase at the department store. Now, before sales tax, these two items cost $130. No sales tax on the pants, 9% sales tax on the briefcase. including the sales tax. The total was $136.75. So what was the price in dollars of the pants? Now, we got pants and briefcase, so let's keep our variables easy, P and B. So just like earlier, we know that P plus B equals this $130. And now our second equation, there's no sales tax on the pants, but there's a 9% sales tax on the briefcase. So in order to do that, 1.09, right, we want to add 9% to it, times B, equals this 136.75. Now, what we want to do, see how before sometimes it's helpful to use substitution in the other one. I thought that was the best way, but now just looking at it, when I stack these problems, well, both of these have P, so I can just subtract these. What I'm going to get is 1B minus, or P minus P is 0, so these are going to cancel. 1B minus 1.09B, that's going to be negative. And then when I subtract these two, get negative 6.75, divide both sides by 0.09. Okay, and we get that B is equal to $75. Now, very easy to go back and plug that in. So the pants will cost blank amount of money if the briefcase costs $75. So I just subtract 75 from 130, and I get that the pants cost $55, which would be what I would fill in to this problem. Example of the video, I wanted to include another break-even problem because they can be intimidating and a little tricky. So let's check this out. Each morning, John jogs 6 miles per hour and rides a bike at 12 miles per hour. His goal is to jog and ride his bike for a total of at least 9 miles. That's important. And in no more than 1 hour. These are going to be important pieces of information that we can use to solve. So if John jogs J miles and rides his bike B miles, which of the following systems of inequalities represents John's goal? So using these variables, right away we want to go at least 9 miles. So we want to jog and bike at least 9 miles. So if it's equal 9, that works. But if it's also 12 or 15, that also works. It needs to be at least 9. So J plus B must be greater than or equal to 9. If I peek at the answers, I can get rid of B and C based on this fact. So now I have to decide between A and D. And right away, both look okay because it's both less than or equal to an hour. And I don't want this to take more than an hour based on his goal. So now I need to decide between A and D. But hopefully, now we at least give ourselves a 50% shot at this. Now, if you take physics, hopefully you're going to learn this. And what we know is that rate times time equals distance. You may have seen the formula V equals D over T. But in this case, we want to solve for time. That's our second variable, right? We want to know what the time is. So in this case, we're going to divide by rate. And we get that time equals distance over rate. Okay? So if John jogs J miles, that's his distance. So J miles is going to be his distance. And his rate of jogging is 6 miles per hour. So J miles, 6 miles per hour. These miles are going to cancel, and when we have a denominator on the bottom of a fraction, that's going to jump up top, and we get J over 6 hours. Okay, and similarly, we could do the same thing where he is riding his bike, but instead of this 6, we would plug in 12 down here, and we would get bike hours. And like I mentioned earlier, we want it to be less than or equal to 1, but based on this process, we now know that the answer has to be choice A.